Xylem is a global water technology leader who works with customers to solve the most critical water and resource challenges. Xylem has more than 17,000 colleagues around the world with diverse water expertise, along with presence and operations in 7 continents. Our products are sold in over 150 countries. We move, measure, analyze, and treat water. We partner with customers to solve their most important water challenges. Our solutions span through the entire water cycle. We bring together advanced technologies, applications expertise, and smart, sustainable solutions. Measurement and control is a segment of Xylem with a revenue of approximately $1.4 million. VTV is a Xylem brand and part of the measurement and control solutions segment, located in Valheim, Germany. Xylem Analytics' largest location with over 400 employees. VTV was founded in 1945, moved from west of Rhön to Valheim in 1954. In 1965, VTV came out with the first dissolved oxygen meter. In 1990, VTV started with the online measurement technology. In 2003, VTV was acquired by Nova Analytics. In 2010, Nova Analytics was acquired by ITT Technologies. And in 2011, Xylem emerged from the spin-off of the ITT Fluid Division, Analytics from ITT Corporation. In 2013, Ebro, another Xylem brand, was integrated and moved to Valheim's location. And in 2016, 4 other brands were integrated in this location and became Xylem Analytics Germany. The VTV Xylem product portfolio includes handheld meters and sensors, desktop devices and sensors, photometry, and biochemical oxygen demand devices. On the process side, the portfolio includes IQ SensorNet, analyzers for river monitoring, and process control, as well as the Multiline 1000 for the monitoring of clean drinking water. Here is an image of the new facility of Xylem Analytics Germany, located in Valheim. And now it is my pleasure to introduce to you Mrs. Susanne Goller, the Senior Product Manager for Photometry and Turbidity. Mrs. Goller is a biologist with more than 20 years of experience in product management and OEM partnerships for photometry and turbidimetry. Mrs. Goller has an extensive background in the field of research and has held various roles in informational technology, including business development in the field of software. Please help me welcome Mrs. Susanne Goller, and I will now turn the meeting over to her.
Thank you, Luis, and thank you, Giovanna. And please tell me if you can see my screen in full screen. This would be nice.
Yes, we can see your screen in full screen now, Susanne.
Yes. Thank you. I want to greet all the audience. So, buenos dias, señoras y señores. And we continue in English. That is much easier for me on turbidity. And this is today's session, and I want to show you the funny world and interesting world of turbidity, which is an underrated parameter for many applications, and this is from water to wine and from environmental to pharma. I will close the video for the moment because eventually it's easier with the sending of the data from my side. So our today's topics will be: what is turbidity? How does it work? So how does turbidity measurement work? And also, what's a special thing about calibration? It is a real image of the world and it's not typical for any other measurement procedure. And then we will have a closer look to VTB turbidimeters, and for sure there will be time for questions. Now, turbidimeter and turbidimeter measurement, you know all in drinking water, because this is where it is required mostly. And turbidity here stands as an indicator for contamination, the status of groundwater, a reference measurement for online and process instruments like sensors, and it is also a quality and process control in the whole step of gaining drinking water. It is an indicator for the contamination of bacteria, bacteria, dirt, etc. Particles in water, and that is what we're measuring with turbidity. We measure particles, are offering surface for bacterial growth, and to make sure that our drinking water is okay for humans and animals, we guarantee the health, and therefore it is an indicator for health assurance as well. But turbidity measurement can be done in many industrial processes, and actually there are many processes you would not even know or think about. So it can be an indicator as like water, but it is also a good tool for quality check and production check. Just to give you some examples, it is in beverage quality, juice, water, wine, soda. It can be all put that the quality of production is fine. It is also in food production an interesting factor. For example, mustard manufacturer here use it to indicate that the washing water between different products is okay, and the washing process has been done successfully. It is an indicator for a carryover of allergens. You know, if people is allergenic and there is a wrong substance in the next production step of food, then this would create a big hassle and they have to pull back products. So here turbidity is a washing water quality check. Chemical products like wall paint, it can be the turbidity level that the wall paint in production is okay. Filter monitoring, here we control that the filter load is okay and there is no filter breakthrough. This usually is done with process or online instruments. And finally, all kind of industries like fuel, for example. We have a motor developer from a big car company who makes fuel tested by our Turb 430, and all suppliers have to use it. Medical applications, for example, expiry of blood bottles, and finally, a huge range of environmental monitoring. But before we come to which product and how is what is the meters for it, we look a little bit deeper into what is turbidity really and how work turbidity measurement. So it is an optical property. So in fact, if you look in a, it's comparable if you would look in a sunlight beam and you see all these little dust particles dancing and turning and being distributed in the air. It's pretty much the same as if you would have a solution with water, etc. And there are particles in, and the behavior is exactly the same. They are twisting, they are in the orientation, turning around. And these particles in a solution, they are causing a scattering of light. And this scattering is different depending on the shape of the particle, the size of the particle, and of the color. Also, the size of the particle will be very important how the scattering takes place. If you look here on the right side, you see that we do have a big particle and a small particle, and depending on the size, the angles of the scattering are different. I don't know if you all like beer, but breweries, for example, they have flakes and yeast, etc. So they have, for example, instruments who do have for big cells like all the yeast, etc., that they do have the 11-degree scattering angle. So this is a special instrument, and we do not provide these instruments, but just to see, turbidity can be used in many applications, and there is many different optical instruments and optics from the instrument and different regulations depending on the application. And we will look closer into drinking water later on. The more particles you have in a solution, the more you have a scattering effect between the particles, which means lower light comes in a certain range to the detector to measure the particle. Therefore, we do not have a linear curve in turbidity measurement. This is done by the meter itself. So the meter is already calibrated from the manufacturer side to this calibration curve in the background. But important is to know that we have a calibration in segments. And you know that because we do have, for example, a 3-point calibration or 5-point calibration, depending on the application. So the most interesting fact is, if you listen to it and you think about other measurements like photometry or pH measurement, it is completely different what we need, because as it is just an optical property, and you just notice, if you look, for example, sand in a water, you know, this is just something which is fading out the light. So turbidity is not comparable to other physical or electrochemical measurement principles. If you think about pH, you have hydrogen protons, which defines pH. And if you think about photometric concentration measurement, you know that there's a clearly defined concentration of a substance like ammonia. So the parameter ammonia is defined by a chemical reaction, and you know exactly how much it is. Turbidity is different. It is not easy to measure our optical property. And so turbidimeters have been developed to make from a optical imagination or a personal impression to go for a more object determination. And that is important to know, to expect the right things to be measured. So what do scattering effects means for measurement? So in terms of readings and reproducibility. If you imagine a piece of paper in front of your hand, you can look at it the full sheet, like here the front view, or you can look at it from the side, which is tiny, tiny and slim. So if you imagine a scattering effect between these both different views from a sheet of paper, you know exactly that a different signal is coming to a detector. And that's pretty much what you have if you have a solution which shows turbidity. So particles are never the same. They move in the solution. So they are not stable. You cannot just say stand still. And therefore, the effect of scattering and the signal at the detector will be different. But we want to have a stable measurement, correct? That we can give a certain, that we have a certain value. So we need to know simply that the values are always oscillating around a certain average value. There is a value, but it's just not stable, if you want to say like that. And in comparison to other measurements, so we have not a defined value, but we will output a frozen value because we do have an average value. And so we count the particles and then we just get the correct value. The more particles are in the solution, so in higher ranges, the lower the resolution and tolerance is given. So actually in drinking water, we can measure with an accuracy of 0.01 NTU because we have few particles and the light is going to the detector. Particles are usually relatively small. In wastewater, for example, they are bigger. And we have also the higher the particle number in a solution is, the more scattering is between the particles. Therefore, the tolerance is becoming higher and also the resolution will be simpler. So for example, we have 157 NTU instead of 157 0.01 NTU. And if it comes to the very high range, we do not even give a digit after the point. So in general, this whole procedure, because we do have these twisting and dancing particles, and also the calibration for particles, which need to be the same as particles. So it's not like a pH standard. Here we have in the total system and measurement principle, we do have higher tolerances than, for example, for other measurement ranges. And important is what we want to have is a quality statement, and particularly if we do in production of food or anything like that, it's not the absolute value which is so important. It's much more a value range, because we want to know our wall paint is okay. So if 600 NTU would be a good wall paint, then we have, it can be 140 to 170, or depending on the application, depending on the manufacturer. Drinking water is regulated, and we come to that. Now, there are different turbidity measurement procedures. So if you look at here, this is our nephelometric measurement, which you and us and everywhere in the world, almost everywhere in the world, or I think everywhere in the world, is used. It is the 90-degree detection of scattered light. So there is a particle which scatters the light in different direction, and we measure our photocell is in a 90-degree angle. We have the light beam passes through, and then this is where we have here the only angle. Laser instruments, by the way, not always offer the same full, correct, complete optical systems. They have 390 degrees in nephelometric, but eventually the light source is different. And this is what we will see next. Transmission, you know transmission very well, because this is done in a photometer as well. So actually I have a lamp, I have the lens is just to, it's an optical precision and bundling instrument. We have the vial, and at the end, so going through directly in 180 degrees, there's the photocell. By the way, this is the turbidity correction of COD, for example, in a photometer. Then we do have a ratio measurement. So ratio measurement, the name is what it says. We do have different angles. This is just an example. It can be all kind of angles, for example, in brewery, also different angles or other applications. And this means I detect several scattering signals at different photocells. And finally, then I do a calculation, an algorithm behind, and then I do a data output. And this makes already clear that a ratio measurement is never the same value as a nephelometric measurement, because we do not have a second detector and we do not have a calculation between two different angles. Why am I telling this so heavily? there is many meters which start to read ratio. So with two different or several angles above 40 NTU. And drinking water, the regulations go up to 40 NTU. So for every other value, it is a ratio measurement. And therefore, you must be aware that they are not comparable. Values are not comparable between a nephelometric measurement with 90° above 40 NTU with those, or above any limitation at that point. And all values should have a mark of ratio, because this means other than nephelometric measurement for drinking water with defined regulations and optics, this is a manufacturer-specific arrangement and detection. So these results are never comparable between different systems. And why is it important to know that? If you have a case study, for example, if you measure drinking water online or in a process, in a river or in a water reservoir, whatever, with higher values, and then you make a reference measurement, and you do have an instrument which doesn't read nephelometric but ratio above 40 NTU, nephelometric values from a sensor which is metrically measuring is never the same as a lab instrument. And a Colombian colleague or customer asked us, yeah, but if my child has fever, I want to read fever no matter which meter. I mean, this is correct. If you measure a temperature of fever, but here we do have different optics, and the only important thing is that you know it and that you measure in the same mode with an optic which is the same. Also, we have different drinking water standards in the world, and as far as I know, Mexico probably is more with white light tungsten, but others are with IR, DIN, EN, ISO. And some countries you can choose. So the DIN ISO technical requirements are a little bit more within a smaller range of specifications. And IR has the advantage itself that already the light source eliminates color effects. You know, if you think about photometers, that color leads to an absorbance in a light source, and at the near infrared and infrared, there the color cannot absorb anymore. So this is why we have a European standard drinking water with IR. White light tungsten, whereas US EPA requirements, they have a white light with a color temperature of the lamp from 2,200 to 3,000 K, and the detector is with a wider angle and must detect between 400 to 600 nanometers. So this can be, in drinking water, it's less problem, but this can be that coloration of a sample, for example, in fruit juices, may disturb and bring other values. And by the way, this means that, for example, if you are measuring fruit juices, you will have a different value between IR and white light, which for a quality proof is not important if you company-specific standard operation is just giving you the value you need. On the other side, fruit juice industry usually use IR, particularly because this color effects. And I want to point out, you know, that there are laser instrument outs as well, which is offering a 360 angle measurement and nephelometric, but usually it today at least does not, as far as I know, does not fulfill standard methods of the tungsten white light. And therefore, if you compare results between different optics, again, the result might differ and be different. We come to the conclusion later on that it's not important, because if you measure water with different optics which are assigned, no matter if IR or tungsten, you will get the same measurement results if you have a standard method and a standard optic for the instrument. But if you're not measuring in water, you can choose the best instrument for your application. And if it's not defined by either, for example, breweries or water regulations or whatever, then we come to the standard operation procedures of a company. And then here you have a choice, which means IR is very good in low-level turbidity. For high turbidity level, ratio is at a certain point a must. Colored samples can be, the coloration effect, the impact of color can be excluded with IR or can be excluded with ratio as well. Small particles are better measured with white light due to the relation of the scattering effect with a small particle at a smaller wavelengths. And big particles can, for example, be measured either better with IR or with brewery specific, for example, 11-degree forward scattering. So the next step, if we want to measure, we have to choose an optic. So if we are in drinking water, we're going to choose the standard regulation drinking water. But then we have calibration. And the calibration is not easy because, or let's say, people were looking for a long time about the correct calibration option. Because what we want to do is we want to have a calibration standard which gives us different formats, different sizes, and unevenly shaped, and that they can be dissolved in a solution. So this was not easy because other than pH and proton, a proton is H+, it's a proton, and you can just make a standard. You cannot easily make a standard for a real world image of particles. So basically, and this is just this is a very good example, and we can imagine it so very well what it means. One of the first turbidimeters, it's I think in beginning of the 20th century, was that they used kieselgur, so diatomy in earth. So algae which have a silica housing, and as you see here in this little picture, they are so different. They can be big, they can be small, and they can be in different orientations within a solution. And that was the very, very first turbidimeter. And here we see already that to find a good standard is not easy. And this first meter, they put a candle under a tube, and then they filled a different level of concentration of these algae with silica housings. And then the fading out of the light was the very first measure. So instead of that a person says, oh, this is pretty turb, or this is less turb, or even if you look at drinking water or water, you wouldn't even see that there are particles in. So to make it less a subjective or personal impression, that was the first meter. Secondly, then in the 50s and later on, we came to the calibration. Standards, and the very first since the 1950s was formacine. To make it short, formacine is a little bit like chewing gum if you have it too long in your mouth. You chew on it, it deforms, and after a while, if it's already getting a little bit in form and shape differently, it may fall apart. So that's a little bit like formacine. And formacine raw materials are not very healthy. The formacine itself is not as bad as the raw material. And then also, depending on the raw material manufacturer, we do have already a formacine between different manufacturers with a variation of 3 to 5%. And then if we do a stock solution, normally 4,000 NTU, it can be already deteriorate after opening from 4,000 to 3,900, 700. So again, and then we make a dilution. So actually, formacine calibration instrument systems, a 10% plus tolerance in the system is normal. And if you look at the US EPA or also DIN ISO regulations, you will see that usually 10% is already stated in standard method regulations that this occurs. And then if we have, for example, formacine and let it stand for a while, if it's a higher concentration, not as bad, but in a small, and it settles. So you have to shake and swivel the glass. And then if you do that, it's falling apart like the chewing gum. And also this is called deterioration. So it will fall apart. And finally, formacine standards, which are freshly prepared, small values are only stable for 2 hours. Today, there are stabilized solutions, but if you haven't opened them freshly, they will deteriorate. We had in our service lab people complaining, also comparing instruments from other companies and saying, oh, we have done the calibration and we have done the measurement and we used a standard, a commercial stabilized formacine of 5 NTU and it's not matching. And then we measured it with freshly calibrated instrument with formacine and with AMCO clear standards, which is the next, the most modern standards. And we found that the stabilized formacine was drifting from 5 to 3.5 or something. So the opening time and the change is, and the distribution in the solution of these particles, if you look at it already, it is just changing and drifting. The modern calibration, and we always talk to remind you about particle images. So we have differently shaped, if you think about a sand cone on the beach, if you think about a flake from the wastewater process after cleaning, if you think environmental man about some algae flakes. So actually we do have different forms and sizes, and polymer standards, it's not only AMCO clear, there are others as well. So it's microspheres. And actually this is a defined bead. This is a defined composition. So smaller particles, bigger particles, different shapes, and each of these, so they are non-hazardous as well. And they can be, since we have a certain set of these polymer sizes and shapes, they can be produced absolutely precise with 1% precision from lot to lot. And there is no dilution faults. And therefore, we do have an overall accuracy in the system. Also, the particle stability in comparison to formacine it's just stable. And also the particle size is stable. Apart from the fact, because it's non-hazardous, you can easily dispose it. And you have a long-term stability of minimum 12 months. And now we come to the interesting fact, if you compare results, for example, in drinking water, and we are very sensible in drinking water about the values. Is it 0.05? Is it 0.2? Is it 0.23? And many of you will know that usually say, yeah, but this meter is giving a completely different result, and this is not the same, and one meter is better than the other. You can only compare instruments if you have all instruments with the same and best freshly prepared formacine standard. Because as I said, if you have different formacine from different manufacturer, you have already a variation. And secondly, if you do not freshly prepare it, then you have a deterioration within 24 hours, particularly for small value, and this is the drinking water relevant value. And even if you have stabilized commercial formacine standards, you must at least use the same, but if they have deteriorated, it already will eventually bring different results. And you must take the same metric, the same mode. So if 1 meter is measuring nephelometric, as we have seen before, the other instrument cannot measure ratio because ratio is to an internal algorithmic calculation of dates, of values. And this is giving a manufacturer-specific result. Now we come to the turbidimeters of VTV. We have a range from portable to lab to process. And I will concentrate on these 2 meters. So the portable turbidity meter 430 and the benchtop meter Turb 750. And to give you a help already ahead, they have more or less the same well-proven, very well-developed optical system. And therefore, in the next slides, I will just show where we have the same optical accuracy precision, and then I will tell a little bit about the differences. Additionally to these meter, we do have a small meter set which is not reliable for drinking water, and also we do have an environmental and outdoor instrument which is going with the benchtop meter of electrochemical and can be simultaneously used together with pH, but it's also not drinking water reliable. We have sets, and we have for the small portable, we have a small benchtop solution. And in process measurements, so online, we have IQ SensorNet, the Visio Turb. So this is where you have it in surveillance of ponds, of eventually river monitoring, etc. And the Turb 750 series, as a lab meter, there are many good reasons to look at it closely as a potential solution. We produce all our meters in Germany, Weilheim. You have seen the little slide from Giovanna. So this is where we are located, close to Munich. And we have absolutely super stuff. We have our construction team, and we do have our production team as well in Weilheim. We have 2 options for the different drinking water standards. So they are European standard and US EPA. So this means there is either a tungsten or an IR model. And it's a very small, powerful lab meter, up to 1100 NTU applications. And you know, all bench size is different. It has a very big optical finesse, which we look into a minute. We have a very extensive, comprehensive AQA for bigger labs like pharma, like medical, like food production, inclusive coming up soon an administration option. And we can go from print, writing, storage to Excel, or even to LIMS. And that as a very reasonable price, a very really attractive price ratio, performance ratio. So in fact, it's nice to look at to see pay only for what you really need. Now, the portable one, this is in the market and well proven, and actually also in governmental big projects already implemented, or as I said, in a big car manufacturer, very well-known racing car manufacturer, as the motor development product, so fuel income quality check. So it's really proven, and it's very intelligent. We come because we do a very, very good measurement. We have a very good measurement procedure, and the same procedure is in the lab meter as well, and in this small meter. It is the same calibration and data handling option, or almost the complete data handling option, like the big lab meter. It is good laboratory practice compliant in with recording, calibration, interval, protocol. It does not have an extensive AQA, but at least the calibration interval. And with a lab station, you have an even smaller bench. You have even a smaller bench solution, which is more economic than a lab meter. We do have always sets, and we do have many cost-free tools for data handling, which are partly on the delivery. So all in all, it's a highly flexible solution and a very economic solution. And the application range really also from drinking water to lab or education, schools, governmental, and as I said, for example, professional pools and monitoring and health surveillance. We have many of these meters in our health departments. And that what I'm telling here is, apart from the optics, is for the lab meter. So we have, as I said, the same optics. We do have a high precision reproducibility and plausibility check, which is also in the small meter, but we do have a big AQA with an extended user administration coming, a 1 to 5 point calibration, which is and quick cal and calibration proof, which is important for bigger labs and service labs. We have a USB, many data management option, and all the cost-free tools, including a PC software. And this one, we can also hand out programmers instructions if you are a bigger organization and you have a special limb system and you programmer wants to pull the data from our meters, you can reach out to Analytic and we will hand that out for them and provide it that you can use it in your labs. It is all about the meters is the simplicity of use. It's really easy to use. We have well arranged, easy to clean, because we are outdoors partly, easy to clean and really a good feedback for calibration. So on call with just a fingertip, you got all the functions you need for multiple calibration functions. So you are just simply very fast and it's intuitive. You get feedback from the screen. And also for the lab meter, we do have extensive AQA option, including, if you need it, IQA papers for easy implementation in your lab environment. To achieve good results, and we have talked about the different principles, the different optical options. Now, we talk about dancing particles in a solution. So not every stable reading, so frozen reading, is necessarily a correct result or finding. And why is it, and what does that mean? Now, as it is, they do not stand still for measurement, and we do want to have a more or less good average. So first of all, we exclude all ambient and internal scattering effects by the build of a real nice light trap in the meter. So the meter is just, which is trans in 180 degree. It's just absorbed also ambient light. This is our special optics, which is achieving this. But also with this IRPC, so intelligent, reproducible, that you have always, that you have, that if you place it again and again, you get the same value, as well as that the values are plausible, that they are good. This is going to be checked during measurement. So we internally measure some readings, we evaluate in the background these values, we eliminate outliers, which means if there is a complete, either it is for accident, too fast moving, or it is too turning, or it is just one big in a whole bunch of small ones. So all these elimination scattering effects, which is resulting from that, and are just giving peaks which are not in the average, that's going to be eliminated, and therefore, and then we just make the output of a data which is then not oscillating and showing this dancing and dangling. And here we have a best reproducible result. So in fact, it means a stable reading. So what you can read here must be the output of a correct result. And you also find these values here. For example, you get also a check that this is a good value. in the data set which is stored or sent to PC. Another increase of precision is very important, and this also applies to apart from the very small case, this applies to our lab and portable meters. We enhance precision by excluding error sources. Many of you know that there are pre-marked vials, but pre-marked vials do not what an indexing process, so marking, putting a mark here in a certain spot. And this is also described in the standard methods. It means that you can place a vial, press start, you move it slightly, you hold press, you start is still pressed, then you release it, and you shall have not a big jump, not if you have 0.02, 0.03, 0.01, that is fine. But if you would have 0.05, for example, then you go for a different spot, because this makes sure that you have the best scratch-free pass. And if you mark it, you just for the next measurements, you are extremely fast and you are extremely precise, because you have the best pass through the vial. And here on the meter, you find a little notch and a little help to align marking where you have found this place. That's where you mark it. And then you need only place the vial on and on and on in the same position. This makes you quick in routine, and this makes you extremely precise. The only thing you have to do if you work with some labels, with some vials, just to prepare them ahead. If you have a single use, so you use it only one time, then you just slightly twist it left and right and see that you do not have the proof jump. And there is a big advantage in comparison to other procedures which are out in the market. First, we do not use the pre-marked vials. I explained it just the slide before. And we do not use silicone oil to mask the scratches, because we detect the scratches when marking and indexing, as it is described in standard regulation, and put not oil on a vial in an optical system. And oil in an optical system, thus, particularly on the vial, is just attracting dirt and dust or fingerprints or whatever. So this always can impact the measurement result. So therefore, we go for the fast and quick measurement solution with the indexed vials, no optics, no soil. Also here, what I said about averaging of values, with the laser technology also, there is an average, but mostly not the exclusion of influence of scratches, because if you turn it 360 degrees and then you make a calculation of all these values in terms of an average or median or whatever measurement, then you have still the slightly influence of scratches. So actually this way is probably in the overall accuracy a little bit higher. And it has the advantage, it is economic, because if you proof it any now and then, you can use those vials very, very long, because you always find a little spot where there's no scratch. And if you mark it, then you use it for the next time. So you should prove it any now and then, and eventually put the mark on a different position. And as I said, if you have a single use of vials, so you use them only once, then you just need to turn it slightly left and right, and then you will get also the best winner. Together with our IRPC measurement, so the evaluation of the value in the background, and then eliminate the outliers, we are very fast in the measurement, and we have a short time of measuring, and therefore even fast, rapid settling samples can be measured eventually, depending on the application, depending on the sample, mostly relatively good. What you have to do is just don't shake, no bubbles. Bubble always, you can imagine bubbles in a solution is leading to any result but the correct. If you just turn it slightly and then you have align it instantly with a pre-marked vial, you are so fast and quick that with a certain level of fastness, you will be able to measure it. If it's really rapid settling, you never get. In general, there is a limit to measurement, but it's depending on the nature and texture of the sample. And this is a user-specific procedure which you can define, and also the value corridor where you say this is acceptable. So this is something you can set up in your office, and you have to test it. But anyway, these outlier elimination leads to a very short measurement time, and therefore also to a reliable chance to measure settling samples, depending on the speed. I skipped that because we talked about reliable calibration already. The only thing which is interesting is that we have a 1.5 calibration. We have a calibration record, and for the lab meter, we have more options to fast access. And all these data will be automatically put to a calibration record, and also with protocol and date, and to be okay to each value which you are storing. And also the calibration AMCO clear standard offer maximum accuracy. I have shown that to you in the calibration paragraph before. So I just leave it in the presentation, then you can read it. But in the moment, we just can skip it. They have advantages to formacine, as we have seen before. Data output can be very interesting for many of you, because you need, no matter if it's a lab with LIMS, or you prefer PC, or if you prefer writing it down or storing it and send it to a printer, any of these options are available. And as I said, on demand, user of LIMS systems can also ask for information to pull the data from the meters directly. So I skip it. I have said it's really just pay what you need, and it has it offers many advantages. I want to introduce, we have a photometry session in about 3 or 4 weeks from now. I just want to let you know that this is our Swiss knife. I say, you all know these nice Swiss army knives. So actually we have a meter which allows colorimetric measurement, so photometric measurement with more than 150 programs, pH and ORP, and it's not Turbidity, it's Turbidity, but only DIN ISO. And this means, and also for fish farming, due to this combination, you can also measure carbon dioxide and free ammonia in the solution. So fish farming, water testing, monitoring, and health surveillance, that's where this meter is also well demanded. And everything which I have, most of it, what I have explained for the Turb 430 is, most of it is also given here, or it's exactly the same turbidity measurement. For optimization in drinking water, because I think many of you are working in drinking water, the easiest way is make the zero calibration with deionized water. For example, if you run out of calibration standard, mark a vial, dispose the water, fill in your sample, rinse it before, but fill in the samples and measure. Then you have the same vial for the same standard. You have the same influences, because glass is never homogeneous, so there are slightly differences in glassware. So if you have the same calibration of the 0 point, and that's the interesting point for drinking water, and use the vial for calibration and sample, you are so top precise. That is hardly to beat. And the second is, I will not go through it completely because you know it mainly. Air bubbles, condensation, Important if you have wells or water from deep wells and it's very cold or very hot, whatever. So basically, it needs to go to a certain temperature, and drinking water regulation talks about, I think, something between 22 to 25, depending on the country and method. Make sure that, for example, with pipetting for other solutions, you do not have a dehomogenization. So eventually it's better to fill it by pulling it, by just filling it into the vial and not pipetting it. Color, as I mentioned, is a point. Fingerprint scratches. So that's all error sources. And do not expect the wrong thing from a turbidity measurement. It is a quality check in water in product. It must be a referencing to process and lab. There might be an offset between lab and process because they have different calibration solutions. But it's not important if your process instruments say 0.17 eventually and your lab meter says eventually 0.7. There is defined simply an acceptable tolerance. If it's an income control, it can be mandatory for your suppliers to work with the same meter. We have that, as I said, with a car manufacturer. Also, if you compare instrument, tungsten, you see here, you cannot measure anything here. If we do an absorbance measurement with undiluted red bead solution, imagine you put that in a tungsten meter versus a value in an IR meter, which is just here at the end, is not measuring absorbance. You will get different results. Either you have an application or a SOP recommendation. Don't worry about an exact value in the same value. You just want to measure quality. And if you have, you just need as operation procedure in your company or in your lab. And this applies also that you know why you are using measuring mode and that you generally have higher tolerances in the system. And with this in mind, you can measure everything. This is really a nice, turbidity is an absolutely interesting parameter for even questions you might solve and have no solution to measure it. And ask to analytic, and we are also supportive. It might be a solution for something you didn't even know, like, for example, expiry for blood bottles in medical application. This is done by a service from us in Germany. I add information where you can have a video. You find a little presentation about turbidity in total, so a little bit more extensive than what we have done. Also, flyers and analytic have all those flyers and information leaflet will give all information you need for sure. Also in from analytic, and well, it's a little bit close to the hour, but there is time for questions. And for the moment, thank you, and we look for questions right now. So I hand over. Did I hand it over already? Yeah.
Thank you very much. So at this time, we will take any questions somebody might have. So if there are any questions, you can just kind of ask them, or you can put them in the chat, question and answer.
I hope it was not too much at 1 hour, for 1 hour.
I don't know. Let me... Pueden ir dejando sus preguntas por medio del chat o en la sección de preguntas y respuestas. I think so.
So maybe I can take the time to just show one more sensor, which will be presented by my colleague Klaus in the electrochemical session. And this is a sensor which runs with the electrochemical instruments. Is not for drinking water, but it can be very interesting for environmental monitoring and deep water. So I have skipped that for now, but I have kept that as a bonus slide in the presentation, which might be interesting and to be looked at in quiet.
I was muted. I'm sorry. So there's one question in the
Yes.
box. Okay, it's in Spanish. So, para una agua residual es necesario hacer un tipo de tratamiento a la muestra. So for residual water, is it necessary to do any kind of treatment to the sample?
Bueno, para hacer esto, normalmente se tiene que mirar que no se tiene condensación ni que la temperatura es en el rango de 20 a 25 de grados y si es y que no se no se mueve demasiado o en ultrasonic si es con mucho aire en la muestra. Is this the answer? Was that okay?
I think so. I don't see anything else. See.
Yes.
Okay.
Mm,
Okay.
I think so.
I don't see any other questions at this time.
Yeah, so as I said, you get these informations and particularly tratamiento, particularly problemas. There is 2 or 3 slides and there is 2 additional bonus slides in the back, which you will find. So
Okay.
it's just a conclusion of this.
I think we have two more questions here. So number one is, hola,
Chile.
para alcohol ¿qué tipo de equipo recomienda?
Más difficult en español.
Sí, I think that's
You
what
will answer it in English.
Yes.
Alcohol depends on the grade of alcohol, and turbidimeters son hechos para agua o solutions de agua, and alcohol muchas veces ya es posible, por ejemplo, vino, pero vino no tiene 90%, no 70%, y yo no sé exactamente, es dependiente, yo pienso que puede ser que 60% de alcohol o técnico, que eso es en el efecto de scattering, no vale, no anda. Perdona, pero yo voy leerlo en Informa Analytic.
Okay. And then one more, we have felicidades, Susana Golor, para niveles altos de turbidez. ¿Cuál es el método de dilución más confiable?
Confiables en qué respecto, bueno, digamos así, todos son buenos y tienen una calibración. Y eso, la calibración es el A y O. Entonces, eso es lo más importante. Y después, depende de la aplicación. Si ustedes están mesurando en agua potable, los estándares, los métodos are, you have the instrumentos son necesarios de nefelometría. And they all, I just switch, it's faster. And they all will have to do the same job. As I mentioned, with all the calibration and the measuring modes, you can achieve better accuracy in the overall measurement. And one person is doing it extremely precise and the other less. One thing is for sure, I can tell for our instruments that the measuring procedure with the elimination of outliers, so the IRPC, shall I still bring up the screen eventually, that the IRPC is, that is achieving together with smart vials and using the same vial for measurement and calibration, that will bring you the best accuracy in low range measurement from drinking water to higher values. Is that what you wanted to hear, or is it more like which mode you would prefer if you are not using drinking water measurement? Sorry. Yeah, as I said, application range. Maybe you can give another information, Rebecca, which would be which you are looking particularly to. There's different options.
Okay, so that's a question from Rebecca, right? Your answer.
Yeah, Rebecca, that was just what you read, I think.
And no, that was the other. Okay, yeah, in the analysis of digestion of metals in drinking water, it must be determined if the sample contains particles greater than 1 MTU. What would be the best technique to determine this level of turbidity?
And this is the application. Fruit juice producers and vegetable producers, they recommend infrared because the infrared doesn't impact the measurement, whereas color does. If you look about an apple juice, if you look about orange juice, if you look about raspberry juice, so they are ranged from orange to yellow to blue, and 400 to 600 nanometer in white light, there is a big peak for reddish, bluish, whatever juices. So you would get a very low value, but by the way, it doesn't matter. One value is small, so if you take a white light, it would be 110, and in an infrared, it would be 700. Fruit juice producers recommend IR. And if you go for example, very small particles, you would take a white light because of this wavelengths between of the white light in the range of visible light and 400 to 600 nanometer detector. So small particles. So that's one. And then sometimes if you have samples which you are not sure, it could be eventually something to have a test with the two different light sources. And if we go to groundwater, as I said, the probe which you can let down for 100 meters and which is reliable to a pressure of 10 bar from my colleague in the electrochemical, this could be the perfect solution for environmental monitoring. And you could connect it to the electrochemical instrument, which is also measuring ORP, conductivity, dissolved oxygen. So for environmental monitoring, you have bigger particles, you have ground, and you have the ability. So I'm sure that analytic will be a good support, give you a good support, and also with testing. And we are always in the background to support analytic or just share our experience. And we also share if we have not done this application yet and to find a solution to eventually test it with you and even go for an application report with you.
Thank you, Susanne.
Okay.
Really quick, back to the question that Pablo Aguilar had on the alcohol concentration. He said here in his comments, the 96% ethyl alcohol concentration.
Yeah, I really, it's a very good question. And I think it's not 100% compatible with a aqueous solution. But I have no experience. That's a typical application question, which I could not answer today, because, and I will go back to our offices and forward if I have an answer, and I will also forward if we must do a test, because it could be that the scattering and refracting index is different, and the optical system is going to water solution. And if the refracting index is different due to the high amount of alcohol, then it can be that it is not possible, but it can also be, if you want to have a quality check, that we just have a different value than water, but this is a reproducible and repeatable reading, then you could use it for quality check. Does that answer the question for now at a good status?
I think so. So, and we are always, as we want to say, please feel free to forward any additional questions to the local distributor there in the local partner, Analytech, and they will forward them on to us, and we will answer them for you if they don't have the answer, certainly.
That's correct. Well, I talk in Spanish. Igual, cualquier información, preguntas, pueden dejarlos directamente en nuestros correos electrónicos. Estaremos enviando información. Creo que ya no hay más preguntas. I think so. It's no more questions. We can end this presentation. Thank you very much, Giovanna, Susanne. And thank you very much for your time. I think so. Okay, thanks.
Thank you very much. Thank you, Jesus and Luis, and thank you very much for attending to everyone. We appreciate it. Thank you.
Thanks for interest and your time.
Excellent day. Bye.
Thank you, Analytic, Luis, and we will come back with that one question.
We'll be in touch.
Okay.
Yeah.
Okay.
Thank you.